colloquium program. Today I'm very happy to introduce the speaker. There is Dr. Spencer Klein, who is a senior scientist at Lawrence Berkeley National Lab. And he's also a research physicist at the University of California in Berkeley. He obtained his PhD at Stanford, working in E+ E- collisions at Mark II. And then after that, he did a postdoc at Boston University, working in the macro experiment, neutrinos. And then he did another postdoc at Santa Cruz, working in cosmic ray showers. And after that, he went to Berkeley, and he's been there since then. Dr. Klein is an expert in a couple of topics in high-energy particle nuclear physics. One is in the topic of today, astrophysical neutrinos. And he is also an expert on photonuclear reactions and hadron structure. And he will talk also about this other topic tomorrow at a nuclear physics seminar at 2 p.m. If you are interested. But today is a colloquium, and we have this is the title, Astrophysical Neutrinos. What do they tell us about cosmic accelerators? So let's welcome Dr. Klein.
Thanks, Daniel, for that nice introduction. I'm very happy to be here and tell you about something that I find very interesting. I'll start out by talking about cosmic rays and neutrinos, then start talking about detector basics, then talk about astrophysical neutrinos, tell you the signal that we've seen, then I'll try and touch on the question of where do they come from, and then I'll draw some conclusions. So cosmic rays are a very old story. They were discovered by Victor Hess in 1912, who got into a balloon like this and ascended to the heavens, and he found out that the radiation that had seen on Earth increased as you went to higher and higher altitudes. In other words, it was coming from space. So since then, the intervening 100 years, we've learned quite a few things about this radiation, but there are still an enormous number of mysteries. This shows sort of a current air shower. This is the Pierre Auger Observatory in Argentina, which consists of about 1,600 stations, these 3.6 meter diameter water-filled tanks. This shows the array. Here I've put Lawrence, Kansas. I tried to do it roughly to scale. And this shows an event. These tanks are 1.5 kilometers apart. The green-filled circles show the footprint of a cosmic ray air shower on the Pierre Auger Observatory. You can see the single event covers an area about the size of Lawrence. This was energy of roughly 10 to the 20th electron volts in a single particle. So from experiments like that, we've measured the spectrum. You can see it here. Roughly, it's quasi-power law over about 13 decades in energy, from about 10 to the 9th eV up to 10 to the 20th electron volts. If you look a little more closely, you can see there's some feature. There's something here called the knee, where the spectrum steepens, and then the ankle where it gets harder. And just a couple points. One is just to give you some scale. This 10 to the 20th electron volts is roughly equivalent to 48 watt seconds. So enough energy to light a 50 watt light bulb for a second, again, in a single particle. Anyway, on the spectrum up to about 10 to the 16th eV, what we see is roughly consistent with these cosmic rays coming from supernova remnants in our galaxy. This is not when the supernova explodes, but after it explodes, you have a strong magnetic field and an expanding shell of gas, give you conditions appropriate for particle acceleration, which might persist for the order of 1,000 years. And we've measured the composition, and it's a mixture of protons and heavier nuclei, and seems roughly consistent with supernovas. At higher energies, it's a big question. We don't think supernovas can produce acceleration strong enough to reach this part of the spectrum. We don't know, so we don't know the source, and that will be a large chunk of the talk. We also don't know the composition, because at this point, the flux is so small, you can't see it with satellite-based detectors. You have to build detectors on the ground like Auger, and essentially you're trying to measure the composition by seeing what dribbles out of the back of a very thick calorimeter. And that's a tough problem.
So most of those measurements are based on charge particle measurements, whereas at higher energy you can
Sorry, so up to here, about here, these are measurements from balloon-based and satellite-based experiments. So you actually have a detector that flies, and the cosmic rays hit that detector.
The detector that's charged or not?
Depends on the experiment. There are many of them measure the charge. I mean, that's how we know the composition charge. There are even some detectors that are sensitive enough to tell you what the atomic number is in addition to the charge. So, you know, and those are really quite exquisite, but then as you move up the spectrum, the quality of the information degrades. So the problem with figuring out where these things come from, is that cosmic rays propagate in the galaxy and also in extragalactic space, so that even if we measure the arrival direction of a cosmic ray here on Earth, we don't know where it comes from because we don't know the details of the magnetic field. And so these three diagrams here show some sort of back projections from the location of the Earth in our galaxy. And you can see at 10 to the 18th eV, it looks just like a random walk. 10 to the 19th eV, things are starting to get straighter in this particular model. And there are others with different assumed magnetic fields. Of course, the stronger the field, the more wandering. 10 to the 20th eV, things seem to point in roughly directions they're coming from. So, of course, the thing you might do is select the highest energy cosmic rays and look for any asymmetries. The Pierre Auger Observatory has done that, and they find, and this is a very recent result, only a few months old, they have found a dipole asymmetry. Cosmic rays are preferentially coming from one direction. It's about a 6.5% amplitude, but finally, after many years, it's above 5 sigma. Direction is far from the center of our galaxy, but it's roughly consistent with the distribution of nearby extragalactic matter. And this is considered, evidence that these cosmic rays are extragalactic in nature. Not a big surprise, but confirmation. So now I want to turn a little bit to acceleration mechanisms. Since if we're going to try and figure out where the accelerators are, it's useful to think a little bit about what they might be. The standard mechanism is something called Fermi Shop acceleration, where you have a particle and it repeatedly encounters shock fronts. And sometimes if it hits the shock front, it will bounce back and get increased energy. Energy might go up by a factor of order 2. And so if you have repeated collisions for the shock front, or multiple shock fronts, you will get some particles accelerated to very high energies. And this fairly naturally predicts a spectrum that goes as e to the minus 2, which is not what we see in the cosmic rays, but it's not ridiculously far off either. Because you need these repeated accelerations, there's sort of two possibilities. One is you might have a circular accelerator, kind of like the Large Hadron Collider. We have a magnetic field that confines the particles, and they kind of go around and repeatedly encounter shock fronts and eventually escape. The other option might be a linear accelerator, where you have a relativistic jet of particles coming out, and particles will go through these jets and encounter multiple shock fronts and be accelerated. And I'll also talk about examples of this later. The reason you would like to study this is with neutrinos. I think I've already said that charged cosmic rays are bent in transit. They also have a limited range, something called the GZK effect. So for energies above about 40 eeV, they will interact with the cosmic microwave background radiation and lose energy. So even if they did travel in a straight line, they wouldn't get very far. Photons also don't get very far. They interact with the cosmic microwave background radiation. In contrast, neutrinos come straight to us, and also the cross-sections are small. This is an advantage in one way. Means they can escape from deep dust clouds. They can get out of fairly thick astronomical objects. The flip side of the small cross-section, though, is that you need a very large detector. So you can try and calculate, if you want to know how big a detector, you need to say something about the neutrino production. And neutrino production in astrophysical accelerators is kind of assumed to be very similar to that in terrestrial accelerators. You accelerate protons, smash them into a target, you get a bunch of pi zeros and electrically charged pions. Pi zeros decay to 2 photons. This will be important a little later for normalization. Charged pions do decay to a muon and a neutrino, and then the muon decays to 2 more neutrinos and an electron. And same thing happens in an astrophysical accelerator. I've showed these shock fronts, but these shock fronts, there's gas in the accelerator, and there are also many photons in the accelerator. So you get beam-gas interactions. Occasionally, the accelerated protons will collide with this extraneous gas or photons, and you get neutrinos in exactly the same way. Looking ahead, I will also point out that cosmic rays coming and hitting the Earth interact in the upper atmosphere and produce a very similar shower and a bunch of neutrinos. These are atmospheric neutrinos, and they are a major background for the search for astrophysical neutrinos. I'll say more about them later. You can also occasionally have cosmic ray protons interact with cosmic microwave background photons, exciting them to a delta, and you again get neutrinos. These are sort of GZK neutrinos. I won't say much about it, but they're kind of neutrinos produced in transit. And one important caveat, most experiments can't distinguish between neutrinos and antineutrinos, and I'll lump them together here. And there are a few caveats you can ask about later. So I've kind of sort of covered how the neutrinos are produced. So there's 2 ways to calculate the neutrino flux. One is you can take the measured cosmic ray density, and you can make some assumptions about how much gas and how many photons there are in the accelerator. And from that, you can calculate how many neutrinos are produced. There's something called the Waxman-Bahcall limit, which is sort of the maximum expectation for opacity 1. I'll come back to that later. The other thing you can do is you can measure the high energy photons. And by high energy, I mean GeV to TeV photons. These are seen by various satellites and ground-based experiments. And you assume the equality of charged and neutral pion productions. This avoids the uncertainties due to the cosmic ray composition, but you have to do a fair amount of extrapolation in energy to get from GeV photons and even low TeV photons to PeV range. Anyway, lots of work was done in these, and these both came up with the conclusion that you needed about a cubic kilometer detector to be able to detect astrophysical neutrinos. And this was sort of the main rationale for the experiment I'm going to talk about called IceCube. So the main constraint to think about for these detectors is that you need a very large detector of order a cubic kilometer. This immediately drives you to a sparse sampling Cherenkov detector using transparent natural media. It's the only thing that's affordable. You could not possibly build something that big. And so what happens is a neutrino will come in, interact in this case, the ice, produce a shower of electrically charged particles. As these electrically charged particles go through the ice, they'll give off Cherenkov radiation. We deploy a set of optical sensors to detect that radiation. You can also go to much higher energies, and people like Dave Besson are working for very high energies, above 10 to the 17th eV. You can look at coherent radio Cherenkov emission. So there are 2 choices for medium. One is ice. Ice has some advantages. It's extremely radio pure. It's very solid, very stable. The disadvantage is that the optical properties are rather complex. Anyway, and that's what IceCube has chosen to do. There are also experiments in the Mediterranean. This shows KM3net that have chosen to use seawater. Here you have some problems. There's a lot of potassium-40 and a lot of bioluminescence. So typically the rates in their phototubes are 10 to 100 kilohertz, which is about 40 to 400 times higher than IceCube. But there are people that think that's the way to go. Of course, the water is much more homogeneous. So as I move into the detector part of my talk, I just want to point out that this, like any large experiment, is a collaboration. There's about 310 collaborators from 52 institutions in 11 countries working on IceCube. And what I'm going to show you is pretty much the amalgam of their work. So this shows a picture of IceCube. It's located at the South Pole, or more precisely about a mile from the South Pole. We've drilled 86 holes in the ice. each of which go down 2,450 meters. On each hole in the bottom kilometer, we deploy 60 optical sensors called optical modules. So the surface, it forms roughly a 1 square kilometer hexagonal grid, and we have a kilometer of depth. That gives us a cubic kilometer. There are 8 strings in the middle called deep core, where the optical modules are closer together. The advantage of this is this gives us a small central region with a lower energy threshold. There's also a surface array called IceTop. There are 162 stations, each of which looks quite a bit like the Auger tanks I showed you earlier, except they're a little bit smaller, and instead of water, we have frozen water, i.e. ice. We started building the construction in 2005. It was completed in December 2010. I'm very happy to say that 98% of the optical modules are working perfectly. Another 1% are functional. Those casualties were almost all during the deployment. We've had 0 DOMs fail in the past 2 years. The other thing that is very impressive, I think, is that the lifetime is well over 99%. Reason for this is clear, because there's no physicists at the South Pole to screw things up. We just have 2 technicians. So this shows IceCube from the air, and the first thing you say is, where is IceCube? You don't see much, and that's because all of the action is below the surface. IceCube pretty much covers all of the region below the skiway. You can see here, this is where the actual South Pole is. This is the main South Pole station. This is Amanda, which is kind of the predecessor for IceCube. And the only things you can see here that have anything to do with IceCube are the drill camp, which contains the hardware we use to drill the holes, and the counting house, where all the cables come to the surface and all the data is assembled. This shows the drill camp. It's essentially a 5 megawatt hot water heater using the latest in car wash technology, cheap but effective. And this shows the business end. We have our 5 megawatt hot water heater. Water comes through a hose, through the hose reel, down, and then we drill our way down through the ice by essentially melting the holes. And this here shows 2 of the IceTop tanks. They're buried flush with the surface and gradually getting covered with snow. And that's basically the top of one station. This shows a picture of one of the optical modules about to be deployed. This shows the crew here. One other point I want to make is that, IceCube, you think about physicists, really an awful lot of the work is highly skilled technical work, particularly the drilling. Most of the drillers we hire are people with oil rig experience. Some also people with Antarctic experience. They're not physicists generally. Anyway, we can drill holes up to 2,500 meters deep, 60 centimeters in diameter. We drill at speeds up to 2.2 meters per minute. It takes about 40 hours to drill a hole. Then we have about another 12 hours during which we're attaching the optical modules to the cables and lowering them away. We also have some special devices on the strings, a dust logger, which measures the optical property of the ice, and a standard candle nitrogen laser. This shows one of the optical modules. It's probably does not seem like such a big deal now, but back when we were deploying it was quite fancy, particularly the concept of being able to deploy complicated electronics a mile below the ice and have it survive indefinitely was a somewhat radical concept. The main action items, there's a 10-inch phototube here, which is read out by a 300 megasample per second waveform digitizer. It's a custom 128 sample switch capacitor array. There's also a 40 megasample per second fast ADC. We have a timing calibration which exchanges signals between the surface and the optical modules. This gives us better than 3 nanoseconds calibration across the entire array. The thing is self-triggering, runs on less than 5 watts of power, includes LED calibration and everything, and it sends packetized digital data to the surface. Really, the way to think about this is almost like an individual satellite. This shows the dust logger, which sends out a pancake of light and then measures how much light is reflected, and it measures the optical, the scattering length of the ice as a function of depth, you can see it's highly variable. There are these rather broad peaks which reflect the amount of dust that was in the ice when it was laid down. Basically, this is 70,000 years ago here, and up the surface is now. There's also, you can occasionally see these very, very thin spikes, which are due to relatively local volcanoes, which will throw up dust into the atmosphere for a couple of years. We need to try and figure out how to deal with that. So we have these models. This shows, this is for scattering and absorption. We measure as a function of depth and wavelength. And you probably wonder, I'm not going to go through all the details. You're probably wondering why I'm spending so much time on this. This is our Achilles heel. I mean, we've spent an enormous amount of time trying to understand these optical properties, and we have a decent understanding now, but it's still one of our larger sources of systematic.
Once during deployment.
We put the dust loggers down about 6 or 8 holes. If you look here, you can see that, so each of these is from a different hole, and you can see that they agree in general, but the details are different. The ice is not perfectly horizontal, and it's also not isotropic. And there's other information, the lasers, LEDs, a lot of information goes into our ice model. So this shows what we're looking for. There's 3 neutrino topologies. Muon neutrinos, basically you have a neutrino interaction, you get a long muon track. As the muon energy increases, the light you get more and more light, and so by measuring the DEDX, you can get an idea of the energy. Electron neutrinos produce small, relatively well-concentrated showers. We have good energy resolution, very poor angular resolution. And finally, the holy grail, which we have not yet seen, are these tau neutrino double bang events. You have one interaction, a tau comes in, and it produces a shower in the ice, and a tau travels a few hundred meters if it's energetic enough, and then decays, produces a second bang. And this is, would be very, very striking if we could see it. So this just gives you an idea of more what we're looking for. This shows the Cherenkov light from a muon. Muon goes through here, gives off light, and you can see the light can travel substantial different distances, say 50 or 100 meters away from the track. So kind of in contrast to what you do at CMS or something, where you measure points on a track, the points we measure are typically from 10 to 100 meters away from the track. It's a somewhat more complicated problem. The other complication is that the muon tracks lose energies by emitting photons, i.e. Bremsstrahlung, E plus E minus pairs, and via hadronic interactions. These are all very stochastic processes, so the light emission is not uniform. This is another thing we're still trying to figure out how to deal with best. But what happens is the muon goes through the track. You get these secondary interactions and photons, which then go and may scatter and occasionally be seen by an optical module. I'll point out that less than 1 photon in a million is actually observed in the optical modules. This, of course, makes Monte Carlos rather difficult and time-consuming. The way we do tracking is we use do a first guess method, where, like, say you have a muon track. One method fits the track to a plane moving at the speed of light and find the direction. This is nice. You can do this analytically. The other method is something called tensor of inertia, where you fit the light, like here, basically to a cigar and find the long axis. Both of these then give us an input to a maximum likelihood method, where we use something called Pandel distributions. I will mention that this is named after Pandel, who was the graduate student who figured this out. And that is a distribution of the arrival time of light at an optical module at a given distance from the optical module. So this is for between the track and the optical module. So this is for an optical module 8 meters from the track. You can see most of the light is direct. It does not scatter. If you look away, this is 171 meters away. You can see the light is typically very delayed, 500 to 1,000 nanoseconds. And so what we do is we plug these into a likelihood function to get the likelihood for a given track hypothesis and find the best one. So this shows actually the result. This is the zenith angle distribution of muons that are seen going through IceCube. These are downward going muons. These are muons for cosmic ray air showers. They're largest for vertically downward going. They drop off and then right near the horizon, and then you can see the data nicely flattens off. And this is neutrinos. And this shows a couple of things. One is we have a very good understanding of the shape of this curve. Tells us our angular resolution is what we think it is. And you can see here, it's pretty clear we have a pretty clean sample of neutrinos. Because if we didn't, then there would be a tail here, and this distribution would not be so flat. The other test that we know what we're doing is to look for the shadow of the moon, again, from 1.5 miles underground. The reason you get a shadow is that the moon absorbs cosmic rays. So you don't have any cosmic rays, so there's no cosmic ray muons coming from that direction. It's a little tough. The moon never gets more than 28 degrees above the horizon. So, it's kind of coming from the side. But we expect and observe a deficit of about 900 events per year out of 28,000 in our canonical box. So about 12 sigma of observation per year. And from this, we learn that IceCube points to within 0.2 degrees of where we think it is. And we see that the angular resolution is better than 1 degree at high energies. And again, the nice thing about this is it's independent of Monte Carlo, pretty much. So from that, let me now talk about neutrinos. We see, I've mentioned these atmospheric neutrinos. These from pion and kaon decay. Again, I'll lump neutrinos and antineutrinos together. These are from pion and kaon decays. These give you a relatively soft spectrum, e to the minus 3.7 below the knee, e minus 4.0 above it. There's also prompt atmospheric neutrinos from charm or bottom decay. This spectrum follows the cosmic ray spectrum. The flux is poorly known, roughly a factor of 2. It's concerns about forward production and non-perturbative components. Anyway, we use shower calculations and simulations to try and deal with both of these. This shows the measurements of atmospheric neutrinos at relatively low energies. This curve here shows the muon neutrino flux. It's measured up to an energy of about a PeV, not in this plot. And the reason is eventually astrophysical neutrinos cause it to turn over. And then these green points here show the new efflux, and it's measured up from about 80 GeV to 6 TeV. And I'm mainly showing this to give you an idea. This is an energy region where atmospheric neutrinos dominate, and you can see that we get what we expect. We even see about a 5% seasonal rate variation for neutrinos coming from Antarctica. So we have these large backgrounds. I've mentioned the atmospheric muons. There's about 500,000 muons to 1 neutrino. Not so easy to get rid of. And then there's these atmospheric neutrinos. There, the ratio depends on energy. There are a bunch of separation strategies. We can look for point sources. We can use energy spectra. The astrophysical neutrinos are expected to be more energetic. Prompt neutrinos are a complication there. We can compare upward going versus downward going neutrinos. We could also look for tau neutrinos, which unfortunately we have not found. So first clear evidence for extraterrestrial neutrinos came in a search looking for extremely high energy neutrinos. We did not find those. We did, however, find Bert and Ernie here. These are both golden events. They have energies right around 1 PeV. They're almost embarrassingly well contained in the detector. I mean, you just can't find anything wrong with them. 1 PeV is too low in energy to be these GZK neutrinos I mentioned, but it's too high in energy to be atmospheric. We estimate the atmospheric background to be less than about 0.1 event. From that, we then said, let's look for more of these. We began a search that started out as a 2-year contained event search. We've continued. We're now up to 6 years using the same techniques. We select high energy events that originate within the detector. That means we take the outer parts of the detector and use them as a veto region. We select events with more than 6,000 observed photoelectrons. This is roughly fully sensitive for electron neutrinos above 100 TeV and gives us about 40% of the detector. sensitive to all three flavors, although in varying degrees. And again, because this veto region, I mentioned atmospheric neutrinos are likely to be accompanied by atmospheric muons. We veto a lot of the downward going atmospheric neutrinos. So out of this search, we got 82 events in 6 years, including Bert and Ernie. 2 of them are obvious backgrounds. Then we did estimated the backgrounds. I've mentioned some of these things are not so well known. We estimated the downward going muon background using the data. We used a separate analysis where we had a 2-layer veto and measured the number of events that were vetoed in one layer versus the other versus both. And from that, we think about 25 plus or minus 7 events are atmospheric muons. We've estimated atmospheric neutrinos from these previous measurements, plus a theory, to extrapolate to energy, and we also accounting for the self-veto measurement I mentioned. We estimate the non-prompt neutrino background to be 16 plus 11 minus 4 events. Prompt neutrinos, we estimated using this Engel-Reno-Sarkovic then standard calculation to be 3 events. Newer calculation gives us about half of that. Best fit is about 1. Any of those things, you can see it doesn't matter much. Compare this with the 82 events, you can see the signal is more than a factor of 2 larger. So to quantify the event excess, we select event, apply another cut, require the events to have energies above 60 TeV. This to eliminate most of the atmospheric muon background. And then we fit the data to a cocktail of non-prompt atmospheric, prompt atmospheric, and astrophysical neutrinos. In the energy range from 60 TeV to 2 PeV, we get a spectrum, which I'm not going to read out. This is probably only relevant for experts. I'll say a little more about it later per flavor. But there's a couple of flies in the ointment. One is, if it were an e to the minus 2 spectrum, you'd get 4 to 8 events in this 2 to 10 PeV energy range. And we don't see that. So there's one of two choices. Either there's an energy cutoff in the PeV range, or the spectrum is softer. Best fit for the 6-year spectrum is e to the minus 2.9 plus or minus 0.3. So relatively softer. And the significance was about 6.5 sigma in the 4-year analysis. It's more now. We have not calculated it. So what does this fit look like? This here shows the zenith angle distribution with upward going neutrinos here and downward going neutrinos here. This shows the atmospheric neutrino background. This shows the atmospheric muons. And this shows the data with the best fit. You can see there's an excess above the backgrounds at all zenith angles, but it's particularly large for downward going events. And that's because the self-veto pretty much eliminates the atmospheric neutrinos, because they would be accompanied by other particles. The other thing you may note is that the astrophysical neutrinos, basically this excess here, tend to be somewhat more upward going. And the reason for that is simple. Tend to be somewhat more downward going. Partly that's acceptance, and partly it's neutrinos getting absorbed in the Earth. This shows the energy distribution. Here we're showing in terms of deposited energy. That's essentially what we see in the detector, assuming it's electromagnetic. There's about 10 to 15% less light if it were hadronic. And of course, for muons that exit the detector, it greatly underestimates the neutrino energy. But you can see the fit looks reasonable. The other thing in moving toward a more detailed fit is a question about the flavor ratio. Now, this is not as definitive as you might think, because even if you start with a single source of neutrinos, like 100% nu E, 100% nu mu, or 100% nu tau at a source, the sources are far away, so they're pretty much fully oscillated by the time they reach the Earth. And the possibilities, standard model possibilities, all pretty much fall along this line here, which shows in one extreme, this is from muon, this is from a damp muon thing where all you get are nu mu, and this is for a muon beam, kind of two extremes. And anything that's far from outside here would be a sign of non-standard model physics. So far, we have no evidence that for anything other than standard model oscillations. And we cannot say anything about the source yet. But in a few years, we may be able to narrow down the source characteristics. So if we assume 50% new, 50% new bar, and a 1-to-1-to-1 flavor ratio, we get this e to the minus 2.9 power law. This blue band here shows the fit. The points show an unfolded spectrum. You can see it looks like a pretty reasonable agreement. This here shows the prompt upper limit. You can see the flux. The spectrum is similar, but because of, we know it's not prompt because of the self-veto effect, which radically breaks the symmetry between downward going and upward going for atmospheric neutrinos. And this blue here shows the conventional neutrinos. So we've also done a statistically independent test. This is also a 6-year analysis using throughgoing muon neutrinos. It's statistically completely independent and mostly systematically independent. It's easy to select a clean upward going new mu sample, good angular resolution, better than a degree. We measure the muon energy by looking at the DEDX. It's a truncated mean, just like is done in wire chambers. But there's a real large uncertainty on the muon on the neutrino energy. Anyway, this shows the result of the conventional fit here, and this shows the points, and the red shows a fit including the astrophysical component. You can see there's a very large excess here, also well over 5 sigma. And this fit here, though, gives a best fit of e to the minus 2.13, which is fairly different from e to the minus 2.9 I showed you on the previous slide. There's a significant tension. We've spent some time trying to figure it out. We do not have really good ideas. One point is that this throughgoing neutrino muon search is sensitive to considerably higher neutrino energies than the contained events. So maybe if it's not a perfect power law, that could explain it. It's also true potentially different. It's a different flavor content. And this is something we're continuing to study. So other point I want to make before I start moving on to physics interpretations is that the neutrino flux is nearly saturated. This line here shows this Waxman-Bahcall bound, which basically corresponds to the opacity 1 for an e to the minus 2 spectrum. This shows our measurement, and I mean, this is a very hand-waving thing, so don't worry about some of this is above and some of it is above. Main point I want to make here is that the neutrino fluxes are about the highest that we could reasonably expect to see. And so, the normal way of, hiding, if you have a model that you want to save is you turn the dials and turn down the neutrino flux. You can't do that here because we've seen this large diffuse flux, and so any source model should explain the diffuse flux. So the question is now turned to where do the neutrinos come from? I want to start here with one interesting event we saw a few years ago. This is a throughgoing muon. It deposited 2.6 PeV in the detector. The muon energy was probably 3 to 5 PeV, and the neutrino energy was likely 5 to 10 PeV. It's a nice track, so we know the direction to about 0.3 degrees. And then if you go and pull out your favorite sky atlas, and you look and what's in that circle here, and the answer is not much. I think quite a few theorists have looked at it, and I think the general conclusion is there's nothing obviously interesting in that direction. And by obviously interesting, I mean all of the list of candidate sources that might explain these hosts for accelerators. So of course we want to do more systematic studies, and I'm going to spend a few minutes talking about that. But first, I thought I needed to give a little warning. Since these PeV events were presented, literally hundreds of theory papers have appeared. Many of them have been, found nothing, but some have presented apparent positive connections with possible source classes. And this is really not surprising. If you look at enough connections, you'll find some. And you have to be very careful about a posteriori and a posteriori probabilities. What I've chosen to do here, with apologies to many theorists, is to focus on IceCube studies. These are all blind analyses. We do not look at the data when choosing selection criteria, and we also try very hard to properly account for trials factors. You know, we know how many different directions in the sky we've looked at. We know how many source classes we've looked at. So first thing is looking at this contained event sky map. These are this 82 events I mentioned earlier with the two obvious background removed. And there doesn't seem to be a lot of sticking up here. And a more rigorous analysis, there's no statistically significant source seen. There's also no connection to the galactic center seen. The biggest excess kind of here is near but not at the galactic center, has a p-value of 77%, i.e. consistent with statistical fluctuations. Another way to put it is, any given sky map will have some hottest point on it, and the question is whether that hottest point is hotter than the random expectation, and the answer here is no. We've also done a 7-year sky map using throughgoing events. Of course, there's a lot more of them. This map has 711,000 events in it of throughgoing muon, mostly lower energy. Most of these are atmospheric neutrinos. And then, in the northern hemisphere, they're mostly atmospheric neutrinos. In the southern hemisphere, they're mostly downgoing muons. We've looked through, there's no significant excesses. I will mention we derived the backgrounds from data at similar zenith angles, but with scrambled azimuthal angles. So there's no sort of Monte Carlo assumptions here in what's significant. It's all from the data. We've done a whole bunch of point source searches. We've calculated flux limits for a bunch of interesting sources, assuming an e to the -2 spectrum. This shows the limits as a function of declination here. And basically, they're what they see. There's no excesses. Many of these limits are interesting for various source classes. We've looked at, we've done an allsky survey, basically asked, are there any hot spots here that are more than we would expect? The answer is no. We've looked at pre-selected sources, and we've also done source stacking, like looking at all of the blazars or supernova remnants that we've chosen and adding them up. We don't see anything. We've looked for gamma ray bursts using GRB's positions and times determined from photon observations. We've looked for periodic or flaring sources. These are either triggered by other observations. That might mean some other observatories say, hey, this particular source was particularly bright during this period. Did you see anything then? We've also done untriggered things, just looking for bursts in our data. We've done comparisons with LIGO gravity wave events. We've combined limits with Antares. And basically all of these have come up negative. Some of them are, and now I'll go through a couple of them quickly and try and just sort of say what the statuses are. So other thing I'll mention, our galaxy contributes less than 14% of the flux. I think I've covered most of the rest of this. So gamma ray bursts, these are bursts of gamma rays, first seen during the Cold War. We didn't know what they were for a long period. We now think that the short bursts are from collisions of black holes with neutron stars or black holes. That's these shorter duration bursts here. And the longer bursts are from the collapse of supermassive stars. These create relativistic jets, which emit neutrinos. If the jets are pointed toward Earth, the neutrinos are relativistically boosted. We know where these are well because we get space and time coordinates from this GCN, GRB coordinates network satellites. We've done a search. I think I'm not going to go through the details, but I'll point out the model predictions are far below the observed diffuse flux, and these neutrinos, GRBs can explain at most 1% of the observed astrophysical flux. We've looked at galaxies. The interesting galaxies are things called active galactic nuclei. These are galaxies with a supermassive black hole at the center. If it's pulling in accreting material, it will be blasting out a relativistic jet, kind of is shown here. There's a whole bunch of, it emits a bunch of different signatures, gamma rays, radio, etc., all of which are emitted at different angular widths. So there's a whole different classification depending on what was originally what was seen coming through the ratio of radio to gamma rays to X-rays, etc. And we now know basically it's a question of how far the Earth is away from this axis, you know, and angular things. The most interesting events are galaxies are these things called blazars, also known as BL-lac objects, where we're looking straight down the jet. This is the case if you're going to see high energy particles from anything. That's probably the one. Also mentioned Mercurian 421, which is the nearest blazar, is known to produce TeV photons. So we've done a study. We've looked at the signal from 862 blazars as identified by the Fermi LAT gamma ray telescope. We did a bunch of different weightings. And we say that if the spectrum's D&D 2.5, the blazars produce less than 27% of the flux seen by IceCube. If the spectrum is harder, either the minus 2.2, it loosens to 50%. So this does not explain what we see, at least not all of it. We think this is the most interesting AGN. There are other classes, but I'm running low on time. I will skip this. You know, this is, you know, indicative. It's obviously not definitive. We've looked at starburst galaxies or other star-forming galaxies. These are galaxies that are rapidly converting gas into stars. Gas will run out on a relatively short time scale compared with this age of the universe. So these are relatively short emitters temporarily, produce a lot of hot young stars. The heavy ones decay, will form and will go through the life cycle and produce supernova quickly. Get a lot of supernova, they produce a lot of cosmic rays. Cosmic rays go through a lot of gas, get a lot of neutrinos. Done an analysis and can explain, this is actually this Keith-Bechtold et al. Combined Fermi and IceCube, and we conclude these can explain at most 20% of the observed IceCube flux. Of course, there's also supernova remnants, where I started. The theory of the strong magnetic fields and plasma and accretion. We know these supernova remnants are sources of TeV photons, particularly these. We also think that there's evidence for that these photons show evidence of hadronic acceleration. Data from W28 and IC443 have a photon spectrum peaked at 70 MeV. That's consistent with low energy pi0 decay. It's considered good evidence for hadronic acceleration. And you know, as I said, you know, this is all very consistent with the observed cosmic rays. We've looked for supernovas. We don't see anything. The upper limits are becoming interesting. The other point to make is, you know, the sky maps, you know, nearby supernova are concentrated in our galaxy, and we don't see an excess of neutrinos coming from our galaxies. So this does not seem particularly likely as the source of the astrophysical neutrinos, and also a point again, you know, does not seem likely to be able to explain the cosmic rays that we've seen. So general conclusion from this, and I apologize for going through quickly, but time is limited. IceCube and Fermi data have eliminated or disfavored many of the most popular neutrino source models as an explanation for the diffuse neutrino flux. We have also done autocorrelation analyses. Essentially, we take all of our neutrinos and plot the angular separations between them, and that tells us that we're seeing neutrinos from a large number of sources, typically at least 50 or 100. This disfavors some models where you have the objects are very, very rare, and you'd only have a few of them. As I said, most of them are not coming from our galaxies. And the question is, what's left? And there are some possibilities. There's non-blazar galaxies, or some specific types of supernovas, or magnetars, but they seem to have weaker physics cases. And I think, you know, the conclusion here is, you know, we may need to think harder about possible sources. Maybe there's multiple types of neutrino sources. That would be kind of, in one level, very interesting, but also kind of painful. It's also possible that the neutrino production might be divorced from cosmic ray production, because that was a lot of our hints came from cosmic rays. But probably we need to think harder. And so before I move to my conclusion, I want to point out IceCube does a lot of other kinds of physics. You can ask me about any of this later. We've measured the neutrino nucleon cross-section from 6.3 to 980 TeV by directly observing neutrino absorption in the Earth. We have studies of neutrino oscillations using atmospheric neutrinos. We've done dark matter searches, limits on high-energy GZK neutrinos. We've done searches for PeV photons. We've done a ton of cosmic ray physics, including some that involves perturbative QCD. We've looked for bursts of low-energy neutrinos from supernova. We've searched for magnetic monopoles and other exotica, and many other things. So, in other words, we have this beautiful data set from IceCube, but we're still happily exploiting it, but we're also thinking about future instruments because much more progress requires something larger. And by larger, I mean maybe 10 times larger. To be able to afford that, it would probably have to have a higher threshold, so it would have a similar amount of hardware to IceCube, similar number of strings. And so what we would like to build is something called IceCube Gentoo. This current iteration has 240 strings covering 7.5 square kilometers, have longer strings, better photomultiplier tubes, and other improvements. It will include a Pingu high-density infill array, you can kind of see here, where the strings and phototubes are very close together. This will give us an energy threshold of a few GeV. We want to use that to determine the neutrino mass hierarchy, and we'll also have a radio detection array for the highest energies. The reason we want the radio detector array is, optical detectors really can't scale too much larger. Just the attenuation length of light in ice is 100, 200 meters. That tells you how far apart you can put the sensors. You'd like something with a longer attenuation length so you can have a sparser array. Radio waves have attenuation lengths to 300 to 500 meters or more, depending on where they are. You get this nice coherent Cherenkov radiation because of the excess of electrons over positrons. So you can get, for neutrino energies above about 10 to the 17 dB, you get a very large radio signal extending up to about a gigahertz. So a number of groups are working on this. GLU, LOFAR, LINOSC, SKA, satellites. There's also efforts at the South Pole, RICE, and now ARA, and then Ariana on the Ross Ice Shelf. We'll skip this and just show you some nice pictures. This shows the Ariana detector. This basically looks like a television antenna, and that's pretty much what it is. Shows the first station. And right now there's a 7-station hexagonal array running 7 months a year. That's when we have sunlight to run it. We set limits. We've observed signals from cosmic ray air showers and are working on a 1,300 station array proposal. So then let me just conclude with some pictures. It shows this is the new station. This shows the old station from Amanda days. Transportation. See these are the current C-17s. This is what these old days C-141. And getting to the pole of these LC-130s that land on skis and various things. And so let me get to my conclusions. The origins of ultra-high energy cosmic rays are one of the great unsolved problems in physics. Extraterrestrial neutrinos can shed light on the origin and composition of UHE cosmic rays. Many detectors are searching for these neutrinos. IceCube was completed in December 2010 and is working very well. We've observed a flux of diffuse neutrinos at a level near the maximum expected. We've seen neutrinos with energies above 5 PeV. We have not been able to associate this flux with any particular source class, and many of the most popular classes are now disfavored or ruled out. We may need to think harder about sources. Next generation experiments may search for radio waves from EHA neutrino interactions with an active volume of 100 cubic kilometers. Thank you.
Thank you very much. Now it's time for questions or comments.
Could you say something about the sensitivity of IceCube compared to Antares or KM3net?
Okay, so Antares is much, much smaller. So it's more, I would say, more than a factor of 10. KM3net there are multiple plans. You know, the KM3net version, KM3net 2.0, which is what they plan to build in the early 2020s, would be about 5 or 6 times larger than IceCube. And because of the water, it will have somewhat better angular resolution. And for certain things, like such as neutrinos coming from the center of our galaxy, it will be probably an order of magnitude better. For other things, it's maybe a factor of a couple better. Size, you know.
So you need to wait 5 years to get independent confirmation on different experiments?
I would say more than 5 years.
Another question? So this is, so in the DOMs that you showed, the photodetector is pointing down.
Right.
So what's the difference in sensitivity between downward going and upward going?
I mean, it depends on the, you know, on what angle. Are you talking about the DOM or for neutrinos?
Yeah, so I mean, if it's looking down, like, what's the difference in sensitivity between a shower going down and a shower going up?
Depends on the shower energy. At high energies, it's pretty much 1-to-1. At low energies, it goes up to about a factor of 5 or so.
So, Spencer, if you, I realize that it must be model dependent, but if you bootstrap from the gamma ray measurements, what spectral index do you expect from neutrinos?
I think it depends on which gamma ray measurement, and generally the gamma ray spectrum, if you ignore, you know, the attenuation of gamma rays because of the interacting with the cosmic microwave background radiation, the spectra should be the same.
So I guess what I'm asking is what is the spectral index for gamma rays?
It depends on the source you're looking at. I think you could find examples anywhere from 2.2 to more than 3.